So welcome to the Winds and Currents webinar series. Today, we're fortunate to have Meghan Cronin, who's going to talk about recent research she's doing on the diurnal cycle of sea surface temperature in frontal regions of the tropical Pacific. And I'll let you take it away, Meghan. Thank you for being here.
Thanks, Sarah. Yeah, it's great to talk to this group. And as this group knows, since we talked last week with the observing air-sea interaction strategy, I co-lead that UN Decade program, OASIS. And last week we talked about OASIS for the satellite community. So if anyone has had any further thoughts about, what kind of how the UN Decade program can help with the satellite community, and we can talk about that as well here later on. Okay, but right now I'm going to be talking about the diurnal cycle of sea surface temperature. Let me actually put this into presenter mode. There, can you see?
That looks like it's the wrong mode. You need to flip screens.
Oh, yeah, doesn't it? Huh. Oh, that's really weird.
Swap displays.
Okay. Let's see if I put it here. Does that work?
That's also the wrong mode.
Okay, I think, let me get out of share mode. I'm sorry. And
Meghan,
yeah.
Just go into the presentation again, just like you did.
Okay.
And you see in the upper left, there's one of the three symbols says swap displays.
Swap displays. Oh, look at that.
Here we go.
Perfect.
So clever. Okay. Oh, right there. Okay, so talking about the diurnal cycle of sea surface temperature in frontal regions of the tropical Pacific. And we have a paper that is under review in Nature Geosciences for this. And we actually got reviews back. And so we're going to be, this is a good time to get feedback for our resubmit for that. Before getting started here, last week, tragically, Mathieu Raoult passed away, had a heart attack, and left a really big hole in the air-sea interaction community. So there is, let's see, Juliet Hermes put together a Google Doc that people can put their memories in. If you guys know him personally, let me know and I can share with you that that link. But I just wanted to just take a moment here to just say how sorry I am to, how sad this is. And let everyone know about this. Okay. So, okay, now back to diurnal cycles. Okay, what is sea surface temperature? Okay, this is a little picture, a cartoon of the top 10 meters and where is sea surface temperature in here. Oftentimes what's measured is the 1 meter, that we often call that the bulk sea surface temperature. The buoys measure at about 1 meter, but the sail drone, which I'll be showing some data from, actually measures it at 0.6 meters. So closer to the surface, but still within this diurnal warm layer. Above the diurnal warm layer, there's a cool skin. And so the skin temperature can really differ from the 10-meter foundation temperature, which is below the diurnal layer, or the bulk temperature, because of these two effects, the cool skin and the diurnal warm layer. But it's really the skin temperature that is felt by the atmospheres and used for estimating fluxes. So why do we care about all these differences? It seems like it's just really fussy. And after all, you know, the diurnal warm layer is just afternoons, it's just a transient, you know, who cares? Well, the thing is that near surface stratification can trap momentum and other properties into the surface, and that can then set up shears. And in some places where, or a diurnal jet, and in regions that are already marginally unstable, say above the equatorial undercurrent along the equator in the Eastern Pacific, you can get shears that penetrate deeper into the water column. You can see that here is that this is showing the temperature in shade, and then the contours are the zonal current or a long wind current anomalies, composites. And this is work done by Jessica Masick et al. 2021. And you can see that these penetrate on a daily basis down to 40 meters or deeper. And that provides a different source of, or another source of turbulent mixing that could be important for maintenance of like the equatorial cold tongue. Why else? This is from Carolyn Clayson and Bogdanoff, 2014. The air-sea heat flux depends on the skin temperature. And in this figure, they're showing the difference between the heat fluxes calculated for using the skin temperature relative to the foundation temperature, averaged over an annual average. And you can see that the differences can be over 10 watts per meter squared in some places. So that's actually really big. The chemists have discovered this. And so Andy Watson et al. Had a paper out in 2020 that looked at if you just applied a cool skin to the sea surface temperature, what happens? It changes the uptake of carbon dioxide by 30% globally, the global uptake of CO2, just by including that mean cool skin effect of 0.17 degrees Celsius, Kelvin. And when they did that, this black line shows the corrected fluxes over this time series, the 20 years, and they can then compare that to the inventory change estimate, or the estimate based upon inventory change. That's the red line. And you can see that it matches that much better than the uncorrected values. So that's really huge. And that's just taking into consideration the cool skin, not the warm layer, but the cool skin. And then Bo Yang et al. Had out a paper that looked at the effect of skin temperature on oxygen concentration, oxygen fluxes, and net community production. And they found that it could make up to a 30% difference in the annual air-sea oxygen flux, and also quite a big difference in the annual net community production by including the warm layer and the cool skin. And the way they did it was by using the ERA5, the ERA5 skin versus the foundation temperature as a correction to the Argo foundation sea surface temperature. Now, the thing about that is, well, I'm going to show that there can be biases in the ERA5 skin temperature correction relative to the foundation. And I do that using this KEO data. So I have out two buoys, the KEO buoy and the PAPA. These are ocean sites reference stations. And you can go there. Here's the link, pmel.noaa.gov/OCS. And, just in the last 5 years, there's been more than 70 peer-reviewed KEO papers using these data. And I encourage broad use of the data and welcome collaborations. So you can get the data by going to that button, and here, it's just click, click, click. You can get the data. You can also get sail drone data by going to that button. And if you kind of go down, you can get computed fluxes. And I'll say you're welcome for doing this, because I know that you are very thankful for me doing this hard work of calculating the fluxes for these buoys and providing the warm layer corrections, or warm layer and the cool skin corrections to these 1 meter bulk sea surface temperatures. And I actually provide those corrections in skin temperature in the fluxes. And so going to, and that's done using the Farrell et al. Warm layer correction. And so this Farrell et al. Is just a very simple linear, it assumes a linear stratification, and then does this very simple bulk heat equation. I'll go into this later, but it adjusts it up to the surface, and also provides a cool skin. But what we put out here, this warm layer correction, is actually this DT warm, so it's the whole warm layer correction, this from the skin down to the foundation, and for the warm layer, and then there's the cool skin. And so that what I'm going to do is compare that warm layer minus the cool skin to the ERA5 skin minus foundation, and also the ERA5 foundation to the KEO foundation. And here we go. So the black line is the KEO sea surface temperature, and the red is the ERA5 foundation temperature. And that actually is really pretty good. I got this from the APDRC website, which I love, love, love. I don't know if Jim Patemra is online, but thank you very much for making this. And so the mean difference between that foundation is that, and the RMS is very good. But okay, when we look at the skin temperature, not so good. And the skin, this is now the skin minus the foundation from KEO is in black, and from ERA is in red. And in wintertime, excellent, but not during the summer. And that's because there's a warm layer at KEO. And the warm layer, diurnal warm layer, can be larger, twice as large as the cool skin during the summer. And that is, these are, I think I did a 31-day smoothing. And so, to all those people who say, oh, that diurnal warm layer is just, it's just transient. It's just in the afternoons. We don't care about it. It does actually come out in a 31-day smooth, so a monthly average. And when I do a climatology for KEO, you can see the it's quite different. It's twice as, the correction is is, changes the sign. So what I want to know is, what are the large scale patterns? I mean, here we've shown that this sea surface temperature diurnal cycle is not really, I mean, it's just an afternoon, but it does rectify into longer time scales. And I want to go into that a little bit more. And also, what are the large scale patterns, and particularly around fronts, and what are the impacts of these on the large scale? So back to the Farrell et al. Model. Here's the cartoon. And the skin temperature is equal to the foundation temperature plus this T warm, and then you take out the cool skin correction. So the first crazy idea I want to go into is using this Farrell model to adjust the bulk sea surface temperature, not to the skin temperature, but to the foundation temperature. Okay, and then the other thing I want to test, and the thing that I should say here is that the buoys measure the foundation temperature at right before dawn. So this diurnal warm layer, it starts at 6 in the morning as being a pretty uniform after all the nighttime mixing and cooling. You have the skin temperature or the cool skin, but the diurnal warm layer is all eroded. So the foundation temperature is measured by the buoy or the sail drone at right before dawn. And we can use that then as a reference for how well we are able to do this. Okay, the second crazy idea is, can we integrate this model for 24 hours to determine the net daily warm layer correction, and then use that to adjust a daily average SST to skin or foundation? Okay, this math, there's lots of math involved, but really it's this is just a 1D mixed layer model with net surface heat fluxes. You have to include penetrative radiation. And you're integrating it from 6 in the morning until 1 day later. And we can, then those become average, the daily averages. And there's then just the time integral. And you do this also for the mixed layer momentum budget. Very simple, just time rate of change is going to be, or the integrated time rate of change is going to be the wind stress, which is a U star squared, averaged over this trapping depth. Now this can come out and become a square of the use of the averaged U star if you include this gustiness. And now this U star is actually the oceanic frictional velocity, but it can be related to the wind stress just by density ratios. Okay, and that trapping depth is determined by a critical Richardson number being 0.65. And so you plug that in and it's very messy, and you get out this equation for the daily net delta T that is all just dependent upon the integrated fluxes and some gustiness. So a couple notes, you only do this when it's stabilizing, 24-hour heat flux. If you think it's destabilizing, then you're not going to get a warm layer, so you don't do this. Gustiness is the variance of the friction. Look, I oversaid that. 24 hours gives you the net diurnal warming associated with the daily. And this can be evaluated analytically. So, okay. Now I'm doing this with the sail drones, and I have to be able to calculate all of those, heat fluxes and wind stress and frictional velocities. And so I'm using the wind stress, the air temperature, humidity, solar radiation, long wave radiation, barometric pressure, sea surface temperature, winds relative to surface currents. And this is our first mission in 2017 that we went down to the equator, 125 west. We went via Spurs, stopped in Spurs. So there was a couple of 3 weeks there at 10 north, 125 west before heading down. So we have to think of this both in terms of a section and in terms of a time series. 10 north was, we were at 10 north for 3 weeks. So this whole part, I think, was at 10 north. And this, what we're looking at is black is the measured temperature, sea surface temperature, and the red is the foundation, the computed foundation temperature. And you can see that it tracks the coldest part, but doesn't get all of these wiggles. These wiggles are diurnal warming. They're not eddies. This is an eddy though. So it's really handy for the sail drone where, we're kind of convoluting time and space. This allows us to pull apart the little wiggles that are associated with a front and wiggles that are associated with diurnal cycle. So now zooming in a little bit more into December, when we had all this big diurnal cycle, we're in the cold tongue there. Actually, before, I want to just note, isn't this interesting that here you are up at 10 north and there's big diurnal cycle, and then you go across the cold tongue and there's you're in a big frontal region and there's no diurnal cycle that whole time. And then suddenly you're in the cold tongue, you're out of the front and picks up again with a big diurnal cycle. Noticing this was what started this whole study. Okay, so here we are at zooming in to the cold tongue, and the black is the sea surface temperature and the red is the analytical foundation temperature computed from the 10-minute data. And you can see there sometimes are these jumps, and what's happening there is that the warm layer model only integrates up to, in the core algorithm, only integrates up to midnight. It doesn't actually integrate to 6 a.m. It starts at 6 a.m. and then it ends at midnight. And so, and then at midnight, it assumes that the sea surface temperature is the foundation temperature. And that's actually not a very good assumption. Midnight sea surface temperature still has effects of the diurnal warm layer, and you really have to get to 6 a.m. To get to that. There are also all errors in each of these variables, and the net surface heat flux are going to be carried forth. So if there's any biases in that net surface heat flux, that could be causing a bias in this foundation temperature. So that's another issue. But it's pretty good. And when we do the daily averages, it also does really quite well. You know, here we are capturing all of these, the low points. And here, the bottom panel, I'm showing the 10-minute difference between the measured sea surface temperature and the foundation temperature, computed foundation temperature from 10-minute data. And then the dashed line is the average of that, the daily average of that. And then the red is the analytical value. And it's, you know, I think that is success. That is really good. We have this, I think we can say that based upon the daily average fluxes, we can using these heat flux, daily average heat fluxes and daily average SST, we can estimate what the daily average diurnal warming is. And so I'm going to do that now with satellites, because then we can map it out really nicely. And I'm going to look at this famous figure from Dudley's paper, and I think Dudley is on the line. Here, this is cold tongue, very cold, equatorial cold tongue, and we see tropical instability waves, which are hydrodynamic instabilities in the ocean, causing these cuspy patterns on the northern edge of the equatorial cold tongue. The warm water, the warmest water in the tropics is actually north of the equator. So that's the thermal equator is in the ITCC, north of the equatorial cold tongue. And then this middle panel shows the Quickscat wind stress magnitude, and it kind of looks a lot like that sea surface temperature, and that's because that sea surface temperature is projecting into the atmospheric boundary layer and affecting the winds. Now, since then, we have these flux products, and including the geofurrow. I'm using the geofurrow 3 flux product. It's based upon satellite data. And so this shows the wind stress magnitude in color with the sea surface temperature overlaid. And then this is the net surface heat fluxes. And again, you see the cuspy patterns in the net surface heat fluxes and in the wind stress magnitude. And so I can actually calculate the Monin-Obukov depth scales, both for the atmosphere and for the ocean. Here, this is what they are. And those give you an estimate of the buoyancy fluxes that are stabilizing or destabilizing the boundary layers. And if that length scale is positive and small, then the fluxes are stabilizing. Okay, and we see that's the case in the equatorial cold tongue, both in the ocean, in the atmosphere, and in the ocean. And so conceptually what's happening, I mean, just think about it like when you have a latent heat flux that is cooling the ocean surface and warming, or sensible heat flux that is cooling the ocean surface and warming the atmosphere. It's warming the atmosphere from below, and that's going to destabilize the atmospheric boundary layer. And also it's going to destabilize the oceanic boundary layer because you're cooling from the top of the ocean surface. And so it's perhaps not surprising that the buoyancy fluxes and the Monarchov length scales are so correlated between the two, although they're different because they're different equations of states, and radiative fluxes work differently in the atmosphere and the ocean, salinity. Any case, this is this big stabilizing flux into the atmosphere and stabilizing into the ocean leads to a very large diurnal cycle, diurnal warming in the equatorial cold tongue. And these are the amplitudes that we would expect based upon this satellite data. And these are large. At 125 west, this is, you know, a degree or so, or half a degree. So now let's look at, we have the tau array, and we can look at diurnal cycles and their seasonal cycles and see how they change. And so I'm looking at eastern, central, and western sites in these three columns, and on the equator at the bottom, then at 2 north, and in the ITCC region at 8 north in this top. And you can see that, you know, you have seasonal cycles shown for the sea surface temperature in red and the air temperature in blue, and then the diurnal cycle amplitude for that month, the climatology for that, each of the months for air temperature and SST. And so a couple of things that you can note here is that, well, the seasonal cycle of SST and air temperature are really pretty close, very stable atmospheric boundary layer at 140 west throughout the annual cycle here. But unstable at 2 north, 195 west. The air temperature is much colder than the sea surface temperature. And that's particularly true when the sea surface temperature is the coldest. That's the equatorial cold tongue. And then the diurnal cycle is you know, pretty strong diurnal cycle, certainly during the warm season when there's not a equatorial cold tongue, but strong diurnal cycle in the equatorial cold tongue on the equator, but in the frontal region, no diurnal cycle in that frontal region. And because I believe it's unstable here, both in the atmosphere and the ocean. Right there, yeah. Okay, and now we have more buoys. We had enhanced buoys at 95 west as part of EPIC, Eastern Pacific Investigative Climate Studies. And we had full fluxes along the entire eastern line, and we had extra buoys, and we had barometric pressure sensor. And so what I'm showing here is the sea surface temperature climatology diurnal cycle for 0 north and 2 north, 95 west. And then actually, before I do that, I want to show you, I have barometric pressure here at 0 north and 2 north. And wow, there's really big semi-diurnal tides going on here. But if you take the difference between these two, the 2 north and the 0 north, or 0 north minus 2 north, a diurnal cycle pops out from this. Even though there's this big semi-diurnal, it's the difference is a diurnal cycle. And with the positive pressure gradient force here, that would give rise to, so the left, it shows you the pressure difference between those two, but the left-hand side, I put into units of momentum forcing, so 1/rho dp dy, in units of meters per second per day. And so this is a half a day, and let's say it has an average of 1 meters per second per day, so that would be an average of a half a meter per second. And we're seeing about that amount of acceleration. It's increasing from minus 0.2, this is the meridional winds anomaly, to 0.2. And so what I think is happening is that diurnal cycle in the sea surface temperature is giving rise, the front in that diurnal cycle is giving rise to a diurnal cycle in the barometric pressure gradient, and a diurnal cycle in the meridional winds. And other authors have said that this diurnal cycle in meridional winds might be part of a diurnal pulsing of the Hadley cell. Now, we don't have full air column measurements. We're not measuring the full circulation of the Hadley cell, but the barometric pressure sensor is an integrated measurement of, and it could be consistent with that. So this is what I have to say here, that a reminder that the warm layer effect and cool skin effect must be added to a foundation sea surface temperature to get a skin temperature. And that you can use the core bulk algorithm warm layer model to extrapolate to the bulk sea surface temperature to a skin temperature and to this foundation temperature, which could be awfully handy certainly for using with sail drones to try to distinguish diurnal cycles from fronts. But there's also lots of other applications that could be really handy for. The Farrell model can be integrated for 24 hours. If you add this diurnal gustiness and a penetrative radiation, and then you can use that as an analytical equation to map these daily warm layer effects. And doing that, we see that the warm layer effect can have large scale patterns. The equatorial cold tongue front acts as a front in both the atmospheric boundary layer and oceanic boundary layer stability. And in the equatorial cold tongue, where those boundary layers are quasi-stable, we get a diurnal warm layer. So finally, we see that this front in the sea surface temperature diurnal cycle associated with the sea surface temperature front causes a diurnal cycle in the barometric pressure gradient, and that is more than enough to cause this diurnal cycle in the surface meridional winds, which perhaps might contribute to this diurnal pulsing of the Hadley cell. So that's it. I will look forward to hearing your comments and questions.
Thank you very much, Meghan. This was fantastic. Questions for Meghan? And maybe while people are thinking of questions, I'll ask some of mine. First, I was struck, you showed Jessica Masick's results with diurnal surface currents. And so I was wondering, how detectable do you think that phenomenon would be from HFR or from space?
Right. Well, it's a couple of centimeters per second.
Over a big area, I guess.
Over a big area and in the composite, but you know, if you're looking at individual events, it could be larger. And I guess I would have to look at her paper. But do you think it's detectable? I mean, what's your signal? How accurate do you think you can be measuring?
If you can average, you can beat down noise. So Fabrice has put in the comments, it's at 10 meters depth. But so the question is also how much is detectable right at the surface?
Right. And I presume it's going to be bigger.
I would think it'd be bigger. Yeah.
Yeah.
How much bigger? Yeah. There's some data that shows that in some places, but that's very interesting paper. I hadn't seen that. So thanks for a lot for pointing that. It's also very nice to combine both the SST and the velocity anomalies together to see the patterns going through. So maybe some models could be able to extrapolate that to the surface at some point, but that's very interesting topic.
Yeah, that slippery surface, diurnal jet.
Yeah.
And I mean, that's also with if you get the stratification from rain puddles too, you could potentially get that.
So I'm sure people must have questions. There's another comment in the chat from Sid, who says Hughes et al. Shows around 0.17 meters per second. So,
right.
I was also going to ask another satellite focused question, which is that you've shown this diurnal cycle. Oh, wait, let me go to the questions because Sid has a hand up.
Thank you so much. Thank you so much, Professor Cronin, for your very interesting work, because I work on a very similar diurnal warm layers and diurnal cycles, especially in a salinity stratified region like the Bay of Bengal. So this actually brings back to a question that how good is the F96 model, the Ferrol model, when you try to map the diurnal warm layers in such very shallow stratified regions, because I don't know, I have a feeling that in such regions, the warm layer has to be trapped within those salt layers. So any comment from your end would be appreciated.
Well, the Ferrol model, I mean, it's very simple, right? There's a lot more complicated models, but it works surprisingly well. I mean, I'd like to hear from other people too. I mean, there's always a balance of, you know, how much complexity you want to get to kind of get that extra, you know, curvature in the profile versus, you know, being able to do it analytically and, you know, operationally. I think it's pretty good.
Because we have some things where we if you start the F96 model with already an initial 5 meter or if 5 meter mixed layer depth, where it's all because of some rain puddle or some very strong mesoscale signal, then your F96 model tends to if you just use the air sea fluxes, then it shows the trapping depth estimates to go down as low as 40 meters or so, but then the stratification is still intact. So how related, like that could also be like a source of error, right, in terms of SST signals.
You're saying that the trapping depth goes too deep, so there's errors in the trapping depth?
Yeah.
Yeah. Well, yeah, that trapping depth is kind of very simplistic. This is only going to work under stabilizing conditions too, right? So we're not talking about turbulent mixing and convective overturning and finding the mixing depth. It's a trapping depth, not really a mixing depth. You know, when I compare, I've done this for Keo, and I've done it for a bunch of buoys. But, you know, showing here with the sail drones, the foundation temperature that comes from that trapping depth estimate does match the coolest part pretty well. You know, it's very simple. There's better ways,
Yeah.
but it kind of works.
Okay. Yeah, sure. Thank you so much.
Okay. I'd like to hear other people's.
It looks like Shen Elipo has his hand up. Go ahead, Shen.
Hi, Megan. Thank you very much for your talk today. Yeah, this is a little bit of an advertisement. Maybe you know already, and maybe some other people in the audience might be interested in. But so the latest product from the Global Drifter program that we released last year has now hourly SST estimates along all the drifter trajectories. And so the product actually gives you the total SST from the drifters as well as the diurnal component directly. And so you can use that to map globally the characteristics of the diurnal cycle. So
interesting.
If anybody you know, has interest in working on that with me, you know, submitted a proposal, didn't get funded, but you know, you can look at covariance between velocity and diurnal, you know, SST from the drifter velocity. So there's a lot that can be done globally, and so maybe that could be, you know, complementary to you know, your line of research. So I'm happy to talk about it with you if you want.
Yeah, I think that this ERA5 problem is really worth more investigation and more work, because it's so handy to have these, you know, this product, and, you know, groups like you know, this methodology that Bo Yang was developing for calculating the oxygen flux using that correction. I think there's work to be done, and I think that looking at those global maps of the diurnal warming and having reference for that, and these, you know, methods for calculating it analytically, I think there's good work to be done there.
Megan, I have to ask the routine question we always ask about ERA5 products, which is, I assume the Keo data are on the GTS. So how much is ERA5 assimilating the answer, and how much is it independent? If you had a place where you didn't have data that were properly transmitted, would you get a different answer? We never know the answer, so I don't know if you should.
I know it. It's a real trade-off, and I do put the Keo and Papa data onto the GTS. The WMO number does say that it's a reference buoy and don't assimilate it, but those operational weather centers, they love to assimilate everything they can. ECM, I'm not sure whether this goes into ERA 5, but if it does, it's not enough to pull it down. So the errors could be worse, right?
Well, I didn't realize this about having a reference number where you're instructing people not to assimilate it.
Yeah.
That's a useful piece of information.
Yeah, it's a topic that the ocean sites community has been arguing and talking about for decades. And, you know, we were in a review, and the NOAA program got reviewed, and there was people from modeling centers, and they were very clear, I think, to the NOAA program managers that they wanted to have it on the GTS and to you know, have a little respect for them, that they could use it as they want and in the proper way, and that we should be making the data available to them as easily as possible, and that means through the GTS. So that's what I'm doing, but it does lead to these ambiguities sometimes, because in fact, a lot of the communities don't always tell us whether they're assimilating or not.
Tony has his hand up.
Yeah.
Hi, Meghan. Thank you very much for the very nice presentation. So in your last slide, you mentioned the diurnal oscillation of the Hadley cell, which was suggested by other study as well. I wonder whether that has anything to do with the atmospheric diurnal tide, or is it different process?
Well, I don't know. I don't know enough. I need to do this, especially before we resubmit, because there was reviewers that said, hey, you know, that's kind of a little of a stretch to be saying that you're causing diurnal pulsing of the Hadley cell. So I would like to learn more about diurnal pulsing of Hadley cell and all the different processes and you know, counter processes. But this is one mechanism whereby you get a pressure gradient that is varying on a diurnal time scale because of this sea surface temperature diurnal cycle front. And the timing seems to work out so that, you know, I think that we would need to have more, you know, a full process study and to look at the processes, you know, the full circulation cell to see whether the cell is actually changing as a whole and not just at the surface. But you know,
yeah,
it's one piece of the puzzle.
Yeah. Thank you.
Yeah, anyway, this is actually something that the reviewers did flag. So any comments on that, I would really appreciate.
Yeah, and I'm not the reviewer.
Okay. Yeah.
Well, while you had that slide up, Meghan, one of the things it shows is a peak and trough in meridional winds at just about 4 a.m. And I guess the other side's asymmetric. So I was really happy to see a 4 a.m. peak, since that's about what we're targeting for the satellite at the moment. And that's a time of day that is currently unmeasured in wind satellites.
Careful though, that this is all in UTCC.
Oh,
okay.
right.
So 5.
Oh, yeah, we have to correct the
12,
local time.
Yeah, careful. 12 UTCC is 5.6 local.
Okay.
So 6 a. This is about 6 a.m.
That's
local.
6 a.m. And
Yeah.
so you're 8 hours off of that.
Yeah.
Okay. Look at that carefully then.
Yeah. Yeah, I probably should change this. That was another reviewer comment.
Let's see. We're just about out of time, but I see Luciano Pezzi has a hand up.
Yes, thank you. Thanks for the nice talk, Megan. I don't know if I understood your point. I think that was on the slide number 20 about the suppression of the diurnal cycle around 2 and 4 degrees north.
Mm-hmm.
Is it right?
Yes, that's right.
Yeah.
So between 8 north and 2 north, there was a suppression of the diurnal cycle.
I was thinking about more towards to the front, the sea surface temperature front, and I was wondering if it was caused by the tropical instability waves activity, or even like a submesoscale activity nearby the front. I don't know if it makes sense for you or not, or if you can comment a little bit more about it.
I think that it's one-dimensional processes that are causing the suppression of this diurnal cycle in the frontal region, so that the buoyancy fluxes, surface buoyancy fluxes associated with heat fluxes, are destabilizing in the frontal region.
Mm-hmm.
There could be other processes working as well, but I think that this can explain it.
Okay, thanks.
Well, thank you, Megan. I think we're just at the end of the hour. I have lots more we could discuss, but we can save that for another time. Really appreciate you doing this. A big round of applause for Megan, and I will stop the recording.
Thanks so much.